Some craziness happened and I decided to try it. They're trying to make a somewhat more graphic version. So we'll see how that goes. I thought, oh, it's okay, we'll do an experiment, they're looking very interesting. Now it's like 350. Oh no, usually you do. I mean, revision classes. Oh, I see. Yeah.
This is pretty far.
So this semester was
Pretty far.
How loud are you going to speak?
I'm going to speak loud, but I think it's going to be fine.
I can see the.
Can you
That's
not
what I'm
plug it
saying.
there?
It's good to see.
I thought you do like this.
Why don't you check? Yeah, do that.
They barely know enough. I brought my own copy. Someone attending remotely?
His family, parents, yeah.
Did your slides change much, or?
We're just waiting on Nick.
Next? Yeah.
Yeah, you're right.
can't really do that, right? It's terrible representation. It looks terrible. So, yeah. So, like, it'd be a very bad plan. Like, maybe with enough of those. Yeah, just do like 1,000 moves.
Is this being broadcast in here?
How are you? Antonio, Leslie. Hello.
Hey there.
Do you folks, in ECS, do you want to do private questioning or anything, or just have a public question? How do you guys usually?
We usually do mostly private questions.
Yeah.
So if there's a couple from the audience.
Yeah, and then we'll ask them to leave.
And
Yeah.
then, yeah.
Sounds good. So this is getting broadcast to India?
Was it really? Fantastic.
It's a big place.
It's getting
It's like a
broadcast.
broadcast kind of implies a broadcast, right? What do you think?
It's a narrowcast
Narrowcast.
to a few houses in India.
Hey, Tyler. How are you?
We have a lopsided group.
Do it?
Oh, I think sitting on that side.
Might be more.
It's more.
I don't think you travel far. Yeah, it seems like a pretty good
My husband claims that his high school biology class trained their teacher standing inside of the room. Like they decided that they were only like paying attention to she was only
Well, Cape Cod, every single day you'd be the last to look up. You're trying to keep up.
So we did pretty well for the turnout.
Even when we had eggs.
No, when I had eggs, I woke up at Albert.
No, you didn't. One time, like, Albert came in with eggs before you're ready, and you just didn't wake up. You're like, you're gonna eat it. You're like, oh. And then, like, 5 minutes later, you got up. So my data said that one.
Right, okay. Maybe I've gotten.
So welcome everyone. So it's really a great pleasure and honor to welcome you to the PhD defense of Sudeep Pillai. Sudeep did his undergraduate at Michigan and worked at a startup doing computer vision for motion tracking for a few years, and then came here and did his master's with Seth Teller and joined my group for his PhD. And he's just been a wonderful, wonderful person to have in the group, and I'm really delighted that you could join in today for his defense.
Thank you, John. So welcome everyone. Thank you for being here, taking the time. So I'm going to talk about SLAM-aware self-supervised perception in mobile robots. So today, mobile robots are endowed with rich spatial capabilities that effectively allow them to understand the world and navigate in the world, whether it's autonomous vehicles or mobile indoor robots. This is sort of an example of an indoor mobile robot called PR2 navigating in or reconstructing a world while simultaneously localizing itself within that world. So really what we want robots to be able to do is somehow be cognizant, be aware of where it is in the world, and use that to their advantage for certain perceptual tasks. More importantly, what we really want are mobile robots that are endowed with this SLAM-aware capability that allow them to perform certain tasks where we use SLAM as a supervisory signal for perception. So we look at SLAM as providing a supervisory signal for 3 sort of fundamental tasks. One, object recognition, where we actually use the ability of localization and building a map underneath to somehow inform recognition better than classical techniques. We use SLAM to also provide as a supervisory signal, as I mentioned, where we actually can train models where, if you think about autonomous systems today, they're really growing in terms of the number of sensors that they're using. And the question is, if I were to add a new sensor onto a car, how do I go about effectively using that new sensor in a self-supervised manner? And finally, looking at some of the, sort of inspired by some of the earlier works in spatial cells in sort of the rat hippocampus, we showed that SLAM can actually provide a useful supervisory signal to effectively learn the concept of a visual place. So just to give you a brief introduction of what SLAM is, really it's a state estimation problem where we're trying to estimate the state of the robot given by the latent variable x and simultaneously map the world, which is estimating the landmarks in the scene L. We're essentially given measurements, so the robot is reversible as it moves around, and we want to be able to leverage the measurements to somehow estimate the scene while simultaneously estimate the location of the robot. So really it's represented formally in terms of a directed graphical model where we estimate the joint probability distribution of x and L, which are the state, robot state and landmark, given the measurements U and Z. So really, the factorization of the underlying graphical model allows us to take advantage, allows us to solve the SLAM problem incrementally and extremely quickly or efficiently compared to a full back solution. So really, if you look at SLAM today, the factor graphs provide a more convenient way to represent state estimation, where you can think of the context of visual SLAM, where we're estimating the location of the camera and simultaneously building a map of the world using that single camera. So in the context of visual SLAM, here we can show that we can represent the factor graph for the problem of visual SLAM or other problems that are very robot specific, such as GPS-aided localization, or even post-graph SLAM, where we're essentially estimating just the location of the robot, for instance, as it moves around the world. So what we really want to be able to do is leverage SLAM as a supervisory signal to inform supervision and potentially self-supervision in mobile robots. Really, I want to talk about three contributions in this thesis, and the first one really being, how do you leverage SLAM as sort of a correspondence engine to better inform classical object recognition, where we actually use the robot's understanding of the world to better inform where objects are in the world, as opposed to purely just detecting objects in images. Second, I want to use SLAM as a supervisor signal for self-supervision in robots. And here I'm interested in the task of visual ego motion learning, which is essentially tracing the robot's camera, for instance, over time and self-supervising this task of learning where it is in the world purely from an existing GPS-aided SLAM solution. Finally, we show that we can also learn the concept of a visual place by knowledge transfer, where we use a GPS-aided SLAM solution to learn a metric for visual similarities in images. So really, all these three capabilities, or all these three tasks, take advantage of the fact that we already know how to do SLAM underneath, and how do we use that effectively to perform each of these tasks. So I'm going to talk about the first part of the thesis, which is monocular SLAM-supported recognition. So if you look at recognition today, it's still challenging for robots to effectively localize all the objects within an environment, while simultaneously be able to do this in a real-time manner, a really fast and real-time manner, and also be robust in that I need to know all the objects in the specific scene, while also taking advantage of the fact that implicitly there is some model, there is a fact that the robot is spatially situated in the world. Now, if you were to look at the landscape today, recognition or object recognition has fundamentally changed over the past few years, starting from the original histogram gradients approaches to more recent convolutional neural nets have really changed the landscape in terms of recognition performance for a lot of these tasks. Simultaneously, if you look at the visual SLAM literature, implementations have become significantly more robust. And so the question is, can we actually leverage some of the existing SLAM capabilities that we know how to do in monocular cameras and leverage the existing recognition capabilities that we have to somehow suggest that there is a spatially aware recognition system. So if you look at some of the earlier works in fusing recognition and mapping, most of these approaches really use RGBD sensors. They're limited to indoor environments. They require you to build a very, very rich representation of the world. And it's, in fact, it's fairly limiting the fact that you're using an RGBD sensor for a lot of these tasks. What we really want to do is be able to use a single camera, which makes it significantly more versatile, and track this camera over time so that you can actually detect the objects in its environment while being simultaneously spatially aware of where that robot is or camera is. So today, in terms of recognition, it's really a two-stage process. Initially, the robot, or given an image, you sort of propose object candidates, which are category agnostic. And once you propose these candidates, you classify them using your traditional convolutional neural net, and you classify them into one of k categories with an additional background class. So in this case, the background class is shown in gray, whereas the colored ones indicate that this is what the robot thinks that these categories are. So if you were to look at existing capabilities, there's a lot of false positives. There's very little spatial understanding or memory in terms of every single frame is individually classified. So there's a lot of spurious false positives. It really does not understand where objects are in the physical world, only tries to detect objects in the image. The question is, if you were to provide some implicit understanding of where these objects are in terms of the 3D scene, then maybe you can propose candidates directly in the 3D scene without having to do this in the image. What that allows you to do is now be spatially consistent in that these objects in fact live in some physical world, and these proposals are now classified across each individual frame. The issue here is that it's really not taking advantage of the fact that I'm looking at that same object from multiple views. So the question is, how do you inform recognition from multiple views, not so much as individually classifying each proposal that are spatially cognitive. So really the second piece of this is adding that spatial consistency and being aware of this, essentially classifying this object from multiple views and building the belief of where this object is and what this object is from multiple viewpoints, not so much relying on a single view. So what we refer to as a SLAM-aware solution really is to take advantage of where the camera is at any point in time and also build the underlying map. So if you imagine a robot moving around the scene, as it sees the object from various viewpoints, the idea is to build a map while it's moving, while the camera is moving around, implicitly also track the camera's position over time. Now with more added views, you can reduce the ambiguity of one, where these objects are in terms of the depth of these objects with respect to the camera, but also be able to somehow enforce that multiple views can give you a better recognition capability, or will essentially disambiguate recognition from more than just one view. Now obviously we need to be able to also deal with occlusions, and this is capabilities where if you did maintain a reconstruction of the world, then you can actually in fact take advantage of that capability to build occlusion awareness directly into the system. So what we do is essentially solve a bundle adjustment problem or a keyframe-based visual SLAM solution using existing techniques with an additional semi-dense reconstruction on top of it. What this really gives you is that we can reconstruct the scene in sort of a semi-dense manner, as you can see on the right, and also simultaneously localize the camera over time. So the camera keyframes, as I'm talking about here, are these red frustums where this is the trajectory of the camera, trajectory that the camera takes over time. Really what we're solving here are the state X and L, which are the set of landmarks in the traditional bundle adjustment problem. So we're essentially using an existing technique, which is SLAM, and now treating this as the fundamental representation in order to do recognition. So we first perform a multi-scale spatial segmentation algorithm, which essentially allows you to tease apart objects in the physical world in 3D. And now, given that, I can essentially project each of these views of this object onto the different keyframes that the robots track over time. Now, simultaneously, we can take advantage of the fact that this reconstruction gives you some notion of depth, right? In certain cases, that soda can over there is somehow including the cereal box, in which case we can take advantage of the fact that if I'm going to detect that specific view, then I might see a bit of the soda can, which makes the detector think that I'm seeing a soda can instead of a cereal box. So instead, we ensure that the recognition happens only under a visible set, which allows you to inform recognition much more robustly. So given each of these object proposals, now what we can do is essentially project them onto each of the individual keyframes, and while simultaneously be aware of occlusions in the world. Once these bounding boxes are projected back in the scene, we can now use traditional sort of convolutional neural net feature encoding techniques to describe these each of these individual bounding boxes as feature vectors. And given these feature vectors, now we can essentially probabilistically determine what the label of the object is. The interesting bit here is that not only are we looking at a single view, but we're looking at multiple views. So we want to add that evidence across multiple views. So assuming we use a uniform prior over the category labels, we can actually, and assuming the fact that these features are conditionally independent given the class label, we can now essentially compute the most likely estimate of what that label is given each of those non-including views. And finally, what we can do is reconstruct a scene while simultaneously give you locations of these objects and the categories of these objects directly in the scene. So if you were to just compare, classical technique where on the right showing frame-based detection. So this is purely just showing what the performance is. Given that I know how to propose spatially consistent proposals, how do I classify each individual frame? The question with the issue with frame-based techniques is that because you're classifying each individual frame independently, there may be certain scenarios where that coffee mug over there in one of those views sort of looks like a bowl because it's not really seeing the handle. So what this allows you to do is we're not only relying on a single view, but relying on multiple views to disambiguate the fact that that is in fact a bowl. So on the left, you're seeing the post sort of view aggregated evidence of what that object label is without purely just relying on that single view. Again, we can do this for scenarios where there are occlusions involved. And typically, if you were to propose that proposal for the bowl over there, you're seeing that it's somehow classifying it as a coffee mug. And again, we can take advantage of the fact that these objects, in fact, are occluded by other objects, such as a soda can, which allows you to take, allows you to incorporate the evidence in a occlusion-aware manner. Finally, we show some of these recognition capabilities using, the state-of-the-art fast RCNN with SLAM-supported recognition, which essentially shows you that now we're at that point where we can recover the object label from multiple views and not so much rely on a single view. So if you were to just look at the recognition performance compared to SLAM-aware recognition, even with on that plot over there, you're seeing precision recall of a frame-based detection technique, which is essentially using SLAM-aware proposals with classical, without any form of multi-view aggregation. And with every added view, so 10% and 30% really imply that I'm only aggregating 10% of the views to identify what that object label is. So just with added number of views, you get that diminishing set of returns, but really, even with 10% or 30%, you get significantly better performance over the classical case. So when we had originally developed this algorithm, this was in the pre-RCNN era, so we essentially used VLAN and FLAIR encoding originally to evaluate this on the University of Washington RGBD dataset. Even though it's the RGBD dataset, we only use the RGB so even with SLAM awareness for both scenarios, even with the fast RCNN, we are getting incrementally better performance, despite the fact, purely by having this notion of recognizing it from multiple views. So here, up until now, I've shown you how SLAM can be used at test time, but we can also think of this as using it as a training mechanism by taking advantage of the fact that SLAM actually provides this correspondence engine between multiple views. So if a user were to provide a label, we can use the fact that we know exactly where these objects are to essentially propagate that label onto the reconstructed 3D scene, and then project them back into each of the images while being occlusion aware. So this essentially allows you to propagate labels over multiple views while also mitigating the fact that you don't have the classical label drift. So if you were to just look at the randomized few shot case, where we're essentially using a classifier where we're limiting the amount of training information provided to the detector. In the classical, sort of 2, 5, and 10 shot case, by using a SLAM-aware test time recognition system, we can always improve a poorly trained classifier, for one. But also, we showed that we can train using SLAM awareness, and even in the extreme one-shot case, where we're just giving one single label for every object category, we can now those labels by being SLAM-aware, being vision-aware as well, and still get pretty decent recognition performance just by the ability of being spatially cognizant. So if you were to just compare numbers in terms of what a SLAM-aware one-shot case performs in comparison to the 20-shot case in frame-based techniques, we're able to get similar performance despite the fact that we've considerably used fewer examples. We use considerably fewer examples to do the training. So sort of moving forward, we think that recognition, while it can benefit from the ability to perform SLAM, we think that both SLAM as a system can mutually benefit from recognizing objects in the scene, and these objects are in fact spatially situated within the scene. So here we sort of show a proof of concept of a visual SLAM algorithm running with detections of objects in the scene while being able to simultaneously recover the camera trajectory, while able to recover the camera trajectory and localizing where these objects are in the physical world. So in the solid red line, you're seeing essentially odometry estimates which drift over time, but the camera frustums basically show you how the optimized result does not, just because of the fact that we can incorporate these recognition measurements over time. So I want to quickly move on to the next part of the thesis, which essentially talks about self-supervised learning, where we essentially use SLAM as a memory signal and leverage a GPS-aided SLAM solution to supervise the task of visual ego motion learning. So the idea here is that if I were to strap a camera onto a robot and have the robot drive around in the world, how do you effectively use a camera to learn the task of visual ego motion, which is tracking where the camera is at any point in time, or tracking the robot at any point in time? So the idea here is, as the robot's moving around the world, we want to estimate the location of the camera at any point of time. So really, what we're trying to estimate is a function that takes, say, 2 consecutive images and estimates an odometry estimate from those images, from those sequential images. If you were to piece them together from consecutive images, consecutive pairs of images, now you can essentially reconstruct the camera's trajectory or the robot's trajectory over time. Really, this is done in the sense of formalizing it over a factor graph, where what we're estimating are the robot states, x0 through t, by learning some mechanism to give you this measurement function, u1 through ut. Really, what we're trying to optimize is estimating the robot state x given those odometry measurement factors. So if you were to look at why you would want to do something like learning visual ego motion, one of the issues here is that if you look at existing techniques, most of these solutions require you to have hand-engineered solutions for each different optical type or camera optic, right? In terms of pinhole, fisheye, or catadioptric lenses, what we really want to be able to do is learn a generic function that can learn for varied camera optics. The other concern is that there are several motion constraints in vehicles, for instance, or other robots that require you to specifically gear these solutions to those applications. So the question is, when you have hundreds of sensors or tens of sensors on a car, what happens? Or calibrating these sensors become extremely tedious, and we want some mechanism to learn the task of visual odometry purely by strapping a camera on board and having the robot drive around. So we do this by self-supervision, where SLAM actually provides that supervision for the task of ego motion regression. So really just to recollect, the task is some regression where you're given 2 consecutive images and you want to recover this ego motion or odometry estimate Z, which is parametrized in either SE2 or SE3. What a GPS-aided SLAM solution can give you are long-term trajectories of a robot moving around. And we know how to do this by fusing classical GPS measurements with, say, wheel encoder odometry. So a completely different mechanism to recover very long-term and drift-free robot trajectories. So we first solved the GPS-aided localization problem before we use the fused ego motion trajectory as the target variables for the regression problem. So the idea here is that once we've solved the GPS localization problem on the bottom, well, we're given our images, our sequential images on top, I1 through IT. We recover flow vectors from these sequential images, and now the ego motion regression essentially becomes the task of computing what Z is, the ego motion estimate, given these sequential flow vectors, X. So really what we're trying to show is that we want to be able to learn this as a density estimation problem purely because of odometry in general. There are ambiguities in the solution. So for the same set of flow vectors, it turns out that there are multiple solutions for the exact same flow vector. So the question is, if you were to treat it as a classical regression problem, then the solution either drops to one of these modes, or even the solution does not drop to any of these modes. So the question is, can we actually learn a density estimation problem instead, that we can retain or recover all the modes necessary for ego motion estimation? The other issue, obviously, we're addressing is the fact that because there are varied camera types or camera optics, can we actually build a generic enough model for all 3 camera types and learn to perform visual ego motion? And finally, we actually build a generative model that allows us to introspect the flow given an ego motion estimate. And I'll tell you why this may be important for the context of robots. We propose a conditional variational autoencoder, where the encoder actually is a mixture density network. Now, one of the capabilities of this is that we can capture the nonlinearities in the varied camera optics, whether it's the fisheye or the catadioptric lenses, in the earlier parts of the encoder, and the mixture density network essentially captures the density estimate given the input flow vectors. The encoder here, which is the first half on the left, is essentially recovering the ego motion estimate or density limit Z given the flow vectors, and the decoder tries to recover the scene flow estimate given a sampled ego motion and the location of that feature vector. And I'll get into this in more detail. So the idea here is that we want to be able to use mixture density networks purely for 2 reasons, and the fact that we can capture the nonlinearities, and the fact that we can now parameterize the density estimate in a Gaussian mixture model form. In a mixture density network, the outputs of the network are in fact the parameters of the mixture model, mu, sigma, and pi, which are the mixture, pi being the mixture coefficients. And the idea here is that what we want to minimize is what we've given are essentially flow vectors x and ego motion estimates z. And what we're trying to really minimize is the negative log likelihood under the GMM model, which is referred to as the L and the N loss, essentially. The neat thing about this is that we can also constrain the outputs of the mixture model, where the outputs actually make sense from the context of Gaussian mixture models, in that the mixture coefficients actually sum to 1, and the fact that the variances are in fact positive. And on the decoder side, what we're trying to estimate is the reconstruction of what the flow should look like, given the fact that you're given a ego motion estimate C. So really what we're trying to minimize here is some notion of reconstruction error, given the ego motion, given the fact that I'm moving forward, what should my flow vectors look like, and a variational regularization term to ensure that it does not overfit to the solution. So if we were to do this purely by minimizing the MDN loss, the negative log likelihood, what we'll find out is that specifically for the application of ego motion estimation, it turns out that the overall trajectories that we can estimate, or the estimator that we get, is in fact biased. And the reason is because as the MDN loss incorporates all the individual or sequential flow vectors and the corresponding ego motion estimates, it has no notion of the fact that the robots traveled so much distance. Purely, it's only relying on the fact that these pairs of examples somehow correlate to an ego motion estimate C. So in fact, what we show is that because of this, purely by minimizing the MDN loss, we really get an estimator that is in fact progress, and incorporate an additional global trajectory loss that somehow incorporates the fact that not only am I moving by deltas every so often, but I'm also ensuring that my overall drift is reduced. So what this allows you to do is now predict a very long-term trajectory, or build an estimator that somehow reduces the amount of bias in the estimation model. So what we show is that we can recover the ego motion estimates from all three camera types, and this is sort of an example of the learned visual ego motion or visual odometry from, say, a simulated scene. What we show is that despite the fact that we can do this for all three lenses, the cool thing about this is that we can even provide a generative introspection layer that says what would the scene flow vectors look like if I were to move forward for a pinhole lens, or in the case of the catadioptric, what would the scene flow vectors look like as I move forward, or to the left or to the right. What's neat about this is that all of this is learned just from the data that we provide as self-supervision, not so much as incorporated as models into the system beforehand. So now, once we've learned these ego motion, once we've learned this ego motion model, we can actually use this back into the robot and rely less heavily on the GPS, for instance. So we incorporate these GPS priors more intermittently, so that we can reconstruct very long-term trajectories for very different data sets. So this is sort of comparing the Kitty data set, including the Omnicam and Oxford data sets, which have different types of camera lenses. So roughly, if you look at the numbers, pinhole cameras on average have better performance than the fisheye and catadioptric, and this is still very much a work in progress. I think there's more to really understanding why is it that fisheye and catadioptrics really don't work as well, but we can still recover state estimates fairly reliably. So finally, I want to move to the last piece, which is essentially talking about self-supervised visual place recognition learning in robots. And we are using the exact same mechanism of using SLAM as a mechanism for knowledge transfer, where we use a GPS-aided localization solution to inform or to learn the concept of a visual place. So if you think about what a visual place recognition problem is, or a loop closure detection in the context of robots, the task is given a sequence as the robot moves around the world. We need to somehow identify or extract visual cues from the scene that say that we're in the same place. Now, if we figured out that we're in the same place, what this allows you to do is enforce a constraint that, hey, I1 and IT are in fact the same location, and use that to our benefit to reduce the overall drift incurred in the ego motion estimate, for instance. So really, what we're trying to learn is some function f that extracts these visual cues from images, such that there is some notion of similarity between these two scenes. In the context of the factor graph, this is the exact complement of what we had estimated earlier, where U earlier was the ego motion estimates that we had learned from self-supervision. Now we're essentially trying to learn a mechanism of loop closures, loop closure detection from self-supervision. So again, now that we can solve this, we can estimate the overall trajectory of the robot, given both the ego motion estimates, U, and the loop closure factors as well. So if you look at the visual loop closure recognition and loop closure detection literature, really there's been a lot of work incorporating varied set of techniques for visual description. So all the way ranging from a histogram-based bag of words, whole list and binarized images. Specifically, I'm talking about these implementations on robots, not so much the original implementations for the computer vision sort of literature. FabMap, for one, sort of combines bag of visual words with this approximation that allows them to identify some level of distinctive images. And there have been more extensions with temporal-based sequence SAM, which is essentially instead of matching individual images, how do we match sequences of images so that we can do the same loop closure constraints? The issue with a lot of these is that there are a lot of hand-defined visual, SIFT, SURF, you can name a bunch, and different encoding techniques like bag of words or VLAN or Fisher vectors. And on top of that, there are these hand-designed metrics that you add on top of it to allow you to define some notion of similarity between images. Convolutional neural networks, on the other hand, more recently have changed that landscape altogether. And if you look at Places 205 or NetVLA, they've really learned just by using the traditional AlexNet and ResNet, they've really changed how you can extract visual cues from the image to describe scenes more richly. Now, robotics implementation has quickly sort of followed suit with place recognition with ComNet landmarks by Soderhoff, and even CNN-based place recognition techniques. The issue with a lot of these is that supervising scene recognition is still fairly tedious and expensive, even though they provide rich feature capacity and scalable performance. But obviously, we do need to use pre-trained recognition models to incorporate this. What we're trying to do is essentially learn a new metric for matching, we do this by actually using SLAM or supervision mechanism to enable visual loop closure recognition or learning. So when I mean by learn a new metric for matching, I really am addressing the problem of metric learning. And in metric learning, the idea is that given a set of features that you've extracted from, say, images, the idea is we want to learn some function f that says, bring pairs of examples of images that are in fact taken from the same location closer together, as in similar images that are closer together. And we want to be also able to learn a mechanism, learn that same function where it ensures that dissimilar images, or images taken from different locations, for instance, sit farther away from each other. So really, we can incorporate some penalty on top of, say, the set of similar examples, XQ and XS, or penalize for the fact that dissimilar examples are nearby, or penalize that positive examples, similar examples are in fact far away from each other. We do this with a contrastive loss, where Y essentially provides that supervision, where the first term over there on the left essentially says, bring positive examples closer together and negative examples farther away. Negative examples need to sit farther away from each other with some fixed distance alpha or margin alpha. Now, since convolutional neural nets have become very powerful with describing images, we do the same, but we take advantage of the fact that we have a lot of rich cross-modal information that images and the associated GPS-aided SLAM solution gives you, GPS-aided localization solution gives you. So we know how to define some notion of some metric on the space of poses, where GPS tells you how close images are in the world. And what we want to use that to our advantage to somehow enforce that similar images taken from the same location extract a certain set of visual cues that make them, in fact, fact similar in some new space. So we incorporate this, the supervision that I originally talked about, by being SLAM aware, or by using the fact that we can use this GPS-aided localization solution to provide that self-supervision. Effectively, what this does is we train a Siamese net, which essentially says, given a pair of similar images taken from similar locations and the set of images taken from dissimilar locations, learn a function that tells you that these two images are in fact similar or dissimilar from each other. And we use this by bootstrapping the GPS location. Now, what we use is essentially a pre-trained model for this convolutional net, and provide supervision through this kernel on the bottom, enabled by the GPS-aided localization model. We actually fine-tune the model in that we use a pre-trained Places 365 AlexNet model with shared weights, but we only fine-tune the fully connected layers purely because of the scale of the problem that we're dealing with. If we had more examples or more data, I think there are definitely scenarios where we can learn the entire model from scratch. So just to give you an idea, what this does is, say if a robot were to move around in this St. Lucia, well, we actually have our GPS, the GPS-aided localization problem telling you where exactly you are in the world. So what this essentially gives you is some kernel that says if each of the axes were time, as the robot moves around in the world, the red off-diagonal bands actually tell you that I'm in the same location. So we need some mechanism in images, or we need some mechanism to track visual cues in the images to suggest a very similar kind of similarity matrix, or self-similarity metric. So what we use is we use the GPS-aided localization solution to sample positive and negative examples to feed for the self-supervised contrastive loss. So the idea here is that we want to get to this desired GPS self-similarity metric, whereas if you were to look at a pre-trained ImageNet model, a pre-trained AlexNet model with the Places 365, really it's very hard to tell whether images are in fact similar or not. And so it's very hard to actually build a classifier to suggest that you are in fact in the same location. By training it with the self-supervised mechanism that we propose, we can actually build a new metric where we've learned the fact that where we've learned to extract useful cues, useful visual cues from the images to suggest that in fact we are in the same location. So if you were to just look at an example of what the TSNE embedding of this learned metric looks like, the colors actually indicate what sort of rough visual cue it's extracted from those GPS locations. And we showed that it was fairly consistent in that, as the robot traverses that same scene multiple times, it's somehow embedding the same sort of visual color, which is essentially embedding the same, learning the same, or extracting the same visual cue from those images. So if you were to just compare performance precision recall for I think this is on the St. Lucia data set, we showed that just by fine-tuning, just by the fact that we are providing added labels without any form of supervision provided, we can actually learn to fine-tune a model that improves visual recognition much better than the classical off-the-shelf detector, for instance. And we showed that we can do this, if you compare it on the left, right, we show that even precision recall just significantly improves with the learned metric. So initially, I told you, the metric learning is really bringing similar images closer together and dissimilar images farther away from each other. So here on the left actually shows the visual distance metric. So if you were to look at the histogram of distances of, say, positive labels, or positive similar labels, and negative dissimilar labels, you see that there's a fair amount of overlap. It's hard to disambiguate how to classify negative or positive cases with negative. The learned metric actually has separated those distances significantly more that allow you to build a better classifier on top of the new fine-tuned model. So if you were to just deploy this model on top of if you were to deploy this model on top of the classical factor graph postgraph formulation, the crossed edges here suggest that the images somehow indicate that I've been here before, and we can use this to incorporate loop closure constraints in the classical postgraph formulation. And we solve this to inform that the overall trajectory is in fact consistent over time. So on bottom you're showing the ego motion or odometry drifting over time, which is why the trajectories are inconsistent. Whereas on top you're seeing the trajectories are in fact consistent across a larger time frame, which implies that the loop closure detections are in fact correct. So again, we solved this using the classical postgraph formulation, and we showed that we can do this on multiple data sets where the learned seed embedding is somehow learned a better metric for loop closure detection compared to the classical pre-trained case. So I'm going to wrap up this chapter just by, initially I had somewhat motivated this work by saying, rats learn the spatial cells in the hippocampus. There's some notion of localization, some notion of visual concept learning. And the neat thing about this is that just by, again, doing the TSNE embedding, these are just trajectories off of a Google Project Tango device as I'm moving around Stata. And what it's showing is that as I'm coming back to that same location, I'm somehow extracting features that are in fact suggesting similar visual features from the ones that I've done in the past. So the colors are fairly consistent across multiple loops and trajectories. And I think sort of moving forward, we can even use SLAM to potentially do on-the-fly fine-tuning and not necessarily do this as a batch solve in the back end at train time. So to wrap up, I think what I'm really excited about is that we can use SLAM as some mechanism to self-supervise and even supervise in the context of recognition capabilities. And we think that having spatially cognizant robots really benefit from the idea of bootstrap. And there's still plenty more to be done in this space. I think we might be able to learn a lot more just because of the fact that we know exactly where we are in the world, and we want to be able to use that to our benefit to suggest learning completely from scratch, for instance. So I make 3 contributions. The first being the SLAM supported recognition capability, where we leverage the inherent visual SLAM capabilities in a robot, or a monocular SLAM capability in a robot, to suggest consistent object labels across time. We also show that we can use SLAM in the few-shot object learning case, where we are, in fact, where we use the fact that we are occlusion aware and use this to our advantage to ensure that there is minimal label drift. And finally, we show 2 examples of self-supervision where we use a GPS-aided localization problem to inform, to learn the task of, say, visual ego motion and visual place recognition in mobile robots. So I didn't have too much time to go into this work, which is sort of the 4th piece of the thesis, which talks about a high-performance and tunable stereo reconstruction work that I've done. I really think that in terms of map representations, it's important that folks, especially in the SLAM community, don't do SLAM for the sake of SLAM, and in fact use that representation for other purposes. And this work is sort of trying to push at least in that direction. So in terms of future directions, I think just moving forward, because of the fact that we want to be able to learn from SLAM and learn with SLAM in the loop over time, I think it's important to build spatially and semantically aware databases for robots. I think it's this is just motivated by the fact that if you were to ask a robot, where have I seen artwork before, or show me all views of this specific location, it's important to actually query the robot to understand what the robot actually knows about the world. And this sort of work with Dion on sort of this idea of baking in some of these SLAM capabilities directly on a database level, and then using that to our advantage to do more spatially cognizant queries. And I think even in terms of cross-modal learning in robots, we could potentially use a pre-built map representation to project onto new sensors and learn from experience. Right? This is sort of an example of LiDAR projected back onto the image to potentially learn depth. Or if I knew exactly where I was in the world and what SLAM suggests, then I can essentially learn a mechanism for hindsight lane estimation even, where I'm essentially showing where the robot actually went and projected onto an image in the past. Finally, I think with all this said, simulation also plays an important role, and I didn't really talk too much about it, but I think it's a key capability that we should be able to use simulation to first bootstrap in simulation world or simulated world before we move on to the physical world.
Sorry, wouldn't that second one kind of lead to some problems like going straight for a cyclist?
Sorry?
So at some point the future trajectory went straight for a cyclist.
So in fact,
so
the idea here is that if you had a activity, you can also use the fact to map the world. So if you were to look at sort of the intersection of what you've seen already with that lane estimate, you can actually remove regions where there were objects before. So you can do more than just here I'm just showing one form of projection. There are the robot is sort of cognizant of other things, and we want to be able to use all of those capabilities, not so much just one. So finally, I sort of want to wrap up. I think it's been great working with you, John. You've been extremely supportive, and it's been an absolute pleasure. I think whenever I come talk to you, I sort of get more motivated about just is what you're still. But I think I see SLAM as more of a supervised signal, and honestly, I think I like the fact that we could work together on this, and I came maybe from a different background that made me think differently, and maybe that was good. So I really appreciate it. Nick, I think after my transition, you've been extremely supportive, and I appreciate it. It's your level of enthusiasm. I think at one point we had a conversation, and you said that some of my ideas were cute, and so I wasn't sure what that meant. It was hard to really read you earlier on, but I really appreciate your just enthusiasm with just talking about problems, and I really hope that we can sort of work together even sort of in the near future. Leslie, I tell you, I think taking both of your classes.